In this video, I want to review the test hypothesis topic that I've covered in a previous lecture. Typically, it takes me about 60 minutes or so, almost an hour, full hour, to go through and talk step by step through the test hypothesis. I'd like to do this in about 15 minutes. Just to kind of review, please don't use this in place of those other videos or those other lectures because I went into more detail in those other lectures and it's important stuff. Here, I'm just going to try to summarize it and get us set for our first couple of examples. So the first thing you got to be able to do in a test hypothesis is figure out what it is you want to do. You need to identify the test or formulate the test to conduct. And that test consists of two different hypotheses. We call them a null hypothesis and an alternative hypothesis. And we use the symbols HO and HA, or H naught sometimes the null hypothesis is referred to as. In our confidence interval work, which we've done already this semester, we've tried to estimate a parameter. And the two parameters we typically look at are mu, a population mean, and p, a population proportion. And so there's a parameter that you guys are kind of used to now from things we've done before. Well, the test hypothesis adds two components to that. It adds a specific value, and let me get a pen here. It adds a specific value that we're interested in called the hypothesized value, and it adds a direction that we wish to test. And so the confidence interval might say, hey, let's estimate the average amount of time it takes someone to finish an exam. Okay, maybe we're talking about my students. What's the average amount of time it takes someone to finish exam 2 in my class? Well, that would be a confidence interval question when you're estimating mu. But in a test hypothesis, someone might say, test to determine if it differs from 60 minutes. And so the 60 would be the hypothesized value that you want to compare the mean against, or to. The not equal to, differs from, not equal to, would be the direction of the test. And so we would write mu is equal to 60 as the null hypothesis, and mu is not equal to 60 as the alternative. And typically, what you're going to see is the alternative always has some direction that's not the equal to. The equal to always shows up in the null hypothesis, and the alternative can be one of three choices, actually. It could be the not equal to. You also have the choice of a less than or a greater than test. And we're going to see some examples in some subsequent videos that use the less than and the greater than choices. Things we're used to from our confidence interval days are what I'll refer to now as two-sided confidence intervals. Create an upper and a lower bound for the population mean, create an upper or lower bound for the population proportion. And so if you remember the formulas we were looking at, we always had a z subscripted with an alpha over 2 or a t subscripted with an alpha over 2, meaning if we're 95% confident, we have 5% error, split it and put it in both sides. And that's a kind of the two-sided confidence interval idea. Well, that's equivalent to the two-sided, the not equal to, test a hypothesis. If you wanted to test to see if the mean differs from 60, you'd be interested in seeing if it's above or below two sides, both directions. So we're going to do something very, very similar. However, maybe someone wants to test to see if the mean exceeds 60 minutes or the mean is less than 60 minutes in another example. And so one-sided or one-tailed tests are very much in play now. And so you have to determine the parameter, the hypothesized value, and the direction. Very important in a test hypothesis. We're trying to show the alternative is true. That's what we're hoping to show, but this is the big one here. We need to assume that the null is true. Okay, so in every test that we conduct, we're going to assume that the null hypothesis is true. And because there's an equal sign there, think about what this is saying. This is telling us we're assuming that the population mean is equal to some value. Well, we've done sampling distributions, right? And we've looked at, we don't ever look at mu because we never sample the entire population. We look at X bar. But we've talked a lot this semester about, well, what happens when you move from one sample to the next? That value of X bar is going to change, and we've learned about sampling distributions. And so sampling distributions are kind of in the background. They drove all our confidence intervals. Same thing here. Same sampling distributions are going to be driving our test to hypothesis. So a lot of things we've talked about before, like sample size requirements and assumptions, they're going to be the same for test to hypothesis work that they were for confidence interval work. So a lot of times in this class, students ask me, is the exam cumulative? Is the next exam, does it depend on the last exam? And those are different questions. I won't go back to earlier chapters and put questions on the exam, but the material that we're looking at now depends directly on some material we've looked at earlier this semester. So while the questions won't be cumulative, the topics, the ideas are, if that makes sense to you. I'm a little ahead of myself now. Happens sometimes. Main thing, step one, you got to figure out what it is you're trying to do. State the null and the alternative hypothesis. And once you do that, once you identify the null and the alternative, that's going to take you to a menu in a software program. And that menu is going to do the work. And what work am I referring to? It's going to calculate the test statistic for us. The null hypothesis says we're interested in comparing, or the null and the alternative. The test says we're interested in comparing these two hypotheses. We're going to assume the null is true, but we're really interested in finding out, is the alternative really true? Am I going to reach some information? We call it a contradiction. Am I going to collect some data and reach a contradiction that's going to make me doubt that the null hypothesis is true? So the test statistic is actually the sample data. It's combined in a formula by the computer. You're never going to have to do the math here to give us a number on a printout. And this test statistic you see here is incorrect. It should be X bar. If I remember, I'll go back and make that correction on your copy of the notes, but my copy of the notes is still listed as X. It should be X bar minus mu naught divided by sigma over the square root n. And you may recognize this. I refer to this as the X bar version of the z-score, right? Mu naught is referring to the hypothesized value that you identified in the null and the alternative. And so what we're doing is we're taking a look, how far does the value in our sample, the sample mean, how far does the X bar value fall from the 60 in this case, fall from the value of mu naught? If the null hypothesis is true, if the mean is really equal to 60, we'd expect the X bar value to be pretty close to that. We know it's not going to be perfectly 60, but we would expect it to be somewhere close to 60, so we would expect the z-score to be a relatively small number. We'd expect it to be closer to 0. If the mean is really different from 60, and it could be different in either direction, right? It could be bigger, it could be less than. Well, then we'd expect the value of X bar to be quite a bit different from the 60 as well, because the X bar kind of chases after the mean, the population mean, mu. And so the further mu is from 60, the more likely it is that this test statistic is going to give you a bigger number. Now, it might be a positive number, it might be a negative number, depends where the real value of the mean falls. But the bottom line here is, if the null is true, we expect these things to be close to 0. If the alternative is true, we'd expect them to be bigger, or I shouldn't say bigger, further away from 0, because it could be on the negative side as well. This is true for large sample work. It's also true for small sample work. We've seen both, right? We've seen confidence intervals for large samples and for small samples. We're going to see test hypothesis work for large samples and for small samples. We've talked about the z-distribution quite a bit. We've also talked about a t-distribution. We've talked about n-1 degrees of freedom. Both conversations are going to come up again in our test hypothesis work. So a lot of the issues or topics that came up with our confidence intervals, they're going to come up again. We'll just see them again. Hopefully you did well the last time you saw them. Hopefully you'll do well again. We'll see. But the test statistic we're going to get from the computer. The test drives us to the computer. The computer gives us this number. And now you got to figure out what you're going to do with it. There are two different ways of evaluating a test statistic. The way that makes sense to us now is called the rejection region approach. The future, or the next approach that we'll take a look at, not in this video or not in this lecture, is the p-value approach. And I'll talk a little bit about it with some examples I do, but we're not going to actually take a look at that until a subsequent lecture. Rejection regions, based upon where we've been, what we've done before. Let's see. If the null hypothesis is true, we expect the value to be close to 0, the value of the test statistic to be close to 0. So the further the test statistic is from 0, the more we want to not believe the null hypothesis. So how far would that test statistic need to be? Now, we know that there's random variation with samples we take, and so where would a reasonable value of the test statistic fall? And if you go back to early days in this class, we looked at something called the empirical rule, right? And we said most things fall within 2 standard deviations of the mean. And so we'd say if the test statistic is between plus and minus 2, we don't have a problem with it. And then we learned about the normal distribution, excuse me, And we realized that we can probably be a little bit more precise than approximately 2. And so we've been able to use Z distributions and then T distributions for small samples and come up with very specific ideas. And so let me just explain here. The alpha is the other side of our confidence. If we're 95% confident, our alpha is going to be 0.05. And so with 95% confidence, typically we say this way, at alpha equal 0.05, we reject H naught if this is considered the rejection region. And it has 3 different components. It's first based on the value of alpha. Then it's based also on a sample size. And here, I'm going to assume N is large. What would change if we went to small samples? Well, the Z distribution wouldn't work because the Z distribution is based on the central limit theorem working, which needs a large sample. The other piece that I'm going to assume here is that this is based on a 2-sided test, a not equal to test. Because in a not equal to test, I'm going to put my alpha, I'm going to split it and put it in both tails, much like we did with our confidence interval work. And when you do that, when you put 0.025, that's half of alpha. When you put that in both sides of a Z distribution, you'll come up with the cutoff points, what we now call critical values of 1.96 and negative 1.96. And so what we're saying here, what the rejection region is saying, if the null hypothesis is true, we expect a test statistic between plus and minus 1.96. And so if we see something outside of plus or minus 1.96, then we don't believe the null anymore. And that's typically how we state them. Rejection regions, at this level of alpha, we're going to reject H naught if, and then you have to come up with this piece. And then I'll do some examples. We'll go through it and we'll talk about it. But I've already kind of talked about the 3 pieces. There's an alpha, there's a distribution, and there's a direction. And you got to keep that stuff straight. Okay, so step 1, we say here's the null and the alternative. And if you remember, we had the null hypothesis, the one I kind of threw up on the last screen, was mu is equal to 60 minutes. And then the alternative that I kind of threw over there was mu is not equal to. And again, writing with a mouse is not my strong suit. That's not terrible. I've done a lot worse. Anyway, that's the null and the alternative. We get a test statistic from a printout, and here's our rule. This is the rejection region. So our 4th step says, hey, put it together. Compare the test statistic to the rejection region to decide if the null hypothesis should be rejected. If my test statistic is a value like 3, well, we take a look. Is 3 bigger than 1.96 or less than negative 1.96? Absolutely. Excuse me. Absolutely it is. We're going to reject the null hypothesis. If it was a negative 3, we'd reject the null hypothesis. If it's a negative 2, if it's a negative 1.97 or a positive 1.97, we're going to reject. If it's a 1.8 or a negative 1.8, we're not going to reject. And so that's what the conclusion process looks like. We compare the test statistic that we get from the printout. Remember, we're not going to do the math. We're going to get that from a printout to the rejection region that we've come up with to decide if the null hypothesis should be rejected. So what do they look like? They look like this. At alpha equal 0.05, we either reject or fail to reject the null hypothesis. If you reject the null hypothesis, you see me drawing a rectangle around it up here. If you reject it, if you don't believe the null, what do you believe? Well, you got to believe the alternative. So if you say nope to the null, you got to say yes to the alternative. So if we reject, we're going to say there's sufficient evidence, 2 underlines here, there's sufficient evidence to indicate the alternative is true. If we fail to reject, so if we get a test statistic like 1.7 or negative 0.3, if the test statistic does not fall in the rejection region, then we fail to reject. And if we fail to reject, there is insufficient. And maybe I should choose a different color, just to be clear. Fail to reject goes with insufficient evidence. Reject, there's sufficient evidence to indicate that the alternative is true. What's that mean? Well, in this case, we'd say mu is not equal to 60. And of course, you're going to do that in the words of the problem for me. So you would say the average amount of time that all students take on the exam differs from 60. And so a typical conclusion sounds like at alpha equal 0.05, we reject H naught. There is sufficient evidence to indicate that the average time it takes all students on the exam differs from 60 minutes. And if you fail to reject, you say, we fail to reject. There's insufficient evidence to indicate, and then you say exactly the same thing. This piece here, let me circle it, is just restating the alternative hypothesis in the words of the problem. That doesn't change. That part, the wording that you use here doesn't change whether you're rejecting or failing to reject. The part that changes is this piece here. You're either rejecting or you're failing to reject. World's worst parentheses there, folks. And that part there, there's either sufficient or insufficient. Fail to, insufficient. Reject, sufficient. It's very, very consistent. And the sooner you guys see that, the easier this test hypothesis will become. Now, I know this is going to be extremely unfair of me to do this, but I'm going to do it anyway. You're going to get to a place, hopefully soon, you're going to get to a place where you say, much like we did with confidence intervals, right? There's just one confidence interval idea with a whole bunch of applications. Same thing with the test hypothesis. I'm going to say it's just to test the hypothesis. Now, I know I'm throwing out all sorts of information, and that's extremely unfair of me to do that right now. But trust me, very soon, once you do some problems, once you start to get a feel for this, you're going to be like, oh, okay, I can do that. It's just a test hypothesis. You just got to go through the 4 pieces. And I'll add just one more comment, and then I'll shut this video down. There's 4 pieces. It's just this piece has a second option. And I'll explain that option, or at least I'll point it out to you with some examples I go over in a bit in the next videos. But then we'll come back and we'll take a specific look at what that other option is and how it works and why it works, and quite frankly, why we like it better. So anyway, that's a lot of information. With the program I'm using now, it looks like I'm about 16 and a half minutes or so. You don't know this, but my dog's interrupted me, and so I'm going to have to cut some of that out. But I'll talk to you soon again. So long.